Hi, my name is Amanda Eads. This semester, the project I'm interested in pursuing is related to tongue shape recognition using acoustic and ultrasound data for American English R. So as we've seen in class previously, the image on the left, you have the waveform and spectrogram of the R sound, and I'm wondering whether this can be used to predict tongue shape in that ultrasound image to the right. So this would be what we call a bunched tongue shape. To give you a little bit more insight about English R, so there is acoustic and articulatory variability. So there are several tongue shapes that can be used to produce a perceptually accurate English R. If you look at those top two pictures, the left is what we would call a tip-up retroflex shape, whereas the top right is a bunched or tip down. The tongue tip is curled over. So these are not acoustically perceptually different. But if you do look at a spectrogram or the spectrum in the bottom two pictures, you can see a difference between F4 and F5. So for the retroflex, F4 is lower, and the bunched, the F4 is higher. And so previous work has really focused only on the formant frequency values for these sounds. And so my initial question was, can MFCCs recognize this difference? After talking with the professor earlier today, we think absolutely. So that was my initial project idea, but now I've sort of proposed a model here that's related to my larger overall goal. So the speakers that I have consist of 66 children ages 9 to 15, split across two groups. So there's 30 children with a history of residual speech sound disorder for R. They went through a biofeedback study and learned to produce a perceptually accurate R sound. And then there's a second group of 36 children without history of RSSD. So the acoustic data from our study comes from a syllable repetition task. So there's approximately 45 productions per speaker. These are segmented in prot by syllable and phone. And we have ultrasound data corresponding to the acoustic data. So I've coded around 2,700 images for bunched and retroflex shapes. These are split across the two groups, not quite evenly because of the difference in group sizes. And then the bunch to retroflex image ratio is about 1/3 retroflex to 2/3 bunch. So it's slightly imbalanced. But ultimately, I propose to pursue a TDNN to extract the acoustic embeddings from the acoustic data, a CNN to extract image embeddings, and then put those into a fully connected comparison network to do an LDA between the embeddings to ultimately classify tongue shape, retroflex, or bunched based on acoustic data. So I look forward to your questions. Thank you. And for this class, I'm